This number theory question comes from the European Girls Math Olympiad 2012. Given that P and Q are primes and n is a positive integer such that this equality holds, we are asked to find all possible values of the different Q and P. First of all, we notice that this equation can be written as P plus 1 minus 1 over P plus 1 plus 1 plus 1 over Q equals to 2 n plus 2 minus 2 over n plus 2. This is actually equals to a 1 minus 1 over P plus 1 and 1 plus 1 over Q equals to 2 minus 4 over n plus 2. 1 and 1 is 2, cancel with the 2. And this is equal to 1 over P plus 1 minus 1 over Q equals to 4 over n plus 2. Then this means that Q minus P minus 1 over Q, P plus 1 equals to 4 over n plus 2. This is just a simple algebraic manipulation, and from this step on, there is an important idea behind it. So note that Q has to be greater than P plus 1 from the equation, and both P and Q are primes. The GCD of Q minus P minus 1 and Q is actually equals to the GCD of Q and P plus 1. Since P and Q are primes, the GCD of these two numbers will be also equal to 1. Likewise, the GCD of Q minus P minus 1 and P plus 1 is equals to the GCD of Q and P plus 1. Again, this is equal to 1. It means that the GCD of the numerator here, Q minus P minus 1 and Q P plus 1, it is equal to 1. This means that the fraction in the left hand side is of the simplest form. Then we will see that Q minus P minus 1 is a factor of 4. Now why is it so? Let's say, for example, 3 over 5, they are coprime, equals to x over y, where x, y are a positive integer. Then we'll see that 3 must be a factor of x. And in this case, we know that we can write x as 3k and y equals to 5k for some integer k if x and y are both integers. So back to this question, since it is a factor of 4, so it means that Q minus P minus 1 is either equal to 1, 2, or 4. So Q minus P is either equal to 2, 3, or 5. We are asked to find all possible values of Q minus P. So these are possibly the values. But we need to verify that there exists such P, Q, and N that satisfy this equation. Let me erase this part to get more space. From what we have here, if Q minus P equals to 2, and this is equals to 2 minus 1, that's 1, and Q is equals to P plus 2, and P plus 1 equals to 4 of n plus 2. This one means that n will equals to 4 of P plus 1, P plus 2, minus 2. So in this case, there are many possible cases. Example, P, Q, N equals to 3, 5. When P equals to 3, then Q will equal to 5. And in this case, this is 4 times 4 times 5. That is 16 times 5, which is equal to 80. 80 minus 2, that is 78. So this is one possible solution. And we can check that 57166 is another possible solution. and there are many more. Now we settle q minus p equals to 2. Now if q minus p equals to 3, since both q and p are prime numbers and the difference is an odd number, p must be equal to 2 and q has to be equal to 5. And in this case, sub it in here, 3 minus 1, that is equal to 2, and q equals to a 5, p plus 1 is equal to a 3, and 4 over n plus 2. And therefore, in this case, n equals to 28. So in this case, PQN is equal to 3, 5, and 28. Finally, if Q minus P equals to 5, again this is an odd number, then P is equal to 2 and Q equals to 7. And from the equation here, that is 4 over Q, that is 7, P, that is 3 here, and this is 4 over n plus 2. And n equals to 19. So in this case, PQN is equals to 2, 7, and 19. So with this, we conclude that all the value 2, 3, and 5 are all possible value of Q minus P. With the remark that if Q minus P either equals to 3 or 5, there is a one unique corresponding value of n. But when Q minus P equals to 2, there are many more different values of P, Q, and n. So this is the end of today's lesson. I will see you again. Bye-bye.